there is also a French one, okay? So it's all of this is very common. Anyway.
Does this engine have, this cycle have another name?
Yeah, it has another name. That's what I discovered today, but I don't remember the name. I can look it up. Well, it's some French guy. Yeah, you can just check it out. For French speaking, it is written in this article from French speakers, it's called the such and such cycle. Anyway, the Otto cycle. So what is the Otto cycle? The Otto cycle is looking like this. Is so pressure, volume, is essentially the same as the Stirling cycle, in which instead of having isotherms, we have adiabats. Okay? Now, notice that this Otto cycle is very peculiar because it's not operating between two reservoirs at given temperatures, right? I mean, you don't have a first reservoir, first isotherm with temperature T2, and then another isotherm at temperature T1, unlike the other two cycles that have been shown before. Here, in all 4 points, you will have different temperatures. So that's the point. It's the following. You have an adiabatic expansion. Sorry, you have, well, I have to be careful. So the real Otto cycle starts here. You have first a compression, an adiabatic compression. Then you have an isochoric heating. Then you have an adiabatic expansion. And then you have a cooling part at the same volume. Now, why people started this crazy cycle? Because it looks very similar in spirit, not exactly, to what happens in a car, right? So what happens in a car? You know how a car is working? No, never seen an engine, the engine of a car. So inside a car, there are some cylinders and some pistons that move inside the cylinders, okay? And now, how are these pistons moving? Well, there is an injector, okay, that puts in some fuel. Then there is a compression. Because of compression, the fuel ignites. If you have a diesel engine, the ignition happens because of compression. Essentially, you are compressing it, the temperature raises, and at some point you have an explosion, and the piston goes back. If you have standard, how's it called? A standard engine, a standard fuel, right? Not the diesel, but gasoline. The other one, gasoline. Yes. So if you have a gasoline engine, then you need a spark in order to start the explosion. And that spark is provided by those things that are called candles. Okay? You have ever seen a candle? You put them in spark candles. So you need some electricity in order to start this sparks. But essentially the cycle is always the same thing. You have an expansion, you put the fuel in, then you have a compression. The compression, after the compression you have heating, so you have the explosion process in which the temperature of your system raises up a lot, then the piston goes down, and then the gas goes out, cools down, and then you have the cycle again. So you can feel the pistons. Typically in a car you don't feel all this movement because most of the big cars have an even number of pistons, okay? And if you have an even number, they operate symmetrically. Now, in order to feel this movement in a car, you have to go to a three-cylinder. You have to have a three-cylinder engine. I have one three-cylinder engine. one of my two cars. But you know, ask someone here who has a 3-cylinder engine. If you go in, you will feel that it does. That's because the pistons are operating asymmetrically. You cannot be symmetrical with 3 cylinders. Anyway, so that's what is supposed to describe. So at the end of the day, therefore, when we compute the efficiency of an Otto cycle, we will write it down in terms of something that is called the compression ratio, which is the ratio of the maximal volume to the minimal volume that you're achieving in this compression movement. And if you go to if you read any book that, you know, any sort of brochure about cars, that has, you know, that is listing what are the characteristics of the engine, you will see that there are a few things, the maximum torque, etc., etc., but you might also have information about the compression ratio of your engine that is essentially telling you something about the efficiency. For example, diesel cars have larger compression ratios. I don't remember, but I think it's about probably 20, but I'm not sure. And standard cars, like most of the cars, have 8, 10. So we'll see that it makes a difference when you put it in. All right, so that's it. So how do we now compute the efficiency for this cycle? Well, it's very easy. Now that I gave you a strong motivation to learn the Otto cycle, we can start doing calculations. First, we have an the adiabatic compression. This is the first part of our Otto cycle, this one, okay? So in the adiabatic compression, we have that QAB is equal to 0, and WAB is equal to N times R divided by gamma minus 1, TA minus TB. We have to be careful here because we don't have two temperatures, so we have to keep track of which temperature at which point in the cycle. Now, part number 2 is the isochore. So the isochore, we have WBC equal to 0, and we have that QBC is equal to what? Is equal to CV TC minus TB. Now, typically, CV, I can rewrite it as N times R divided by gamma minus 1. You can easily convince yourself, let us do the little calculation here, that N times R divided by gamma minus 1 is equal to N times R divided by C P minus CV divided by CV, but CP minus CV is equal to R, right? So it's N times CV times R divided by R, and this is CV. Okay, so it's just a way to rewrite the specific heat of the ideal gas. So the heat capacity of the ideal gas. TC minus TB. Then we have the third stroke, which is an adiabatic expansion. QCD is equal to 0. And then WCD is equal to N times R divided by gamma minus 1 TC minus TD. And then 4 QDA is equal to N times R divided by gamma minus 1 TA minus TD. WDA is equal to 0. Okay, notice that QDA is going to be negative, and that's because the temperature at A is smaller than the temperature in D, right? Because you are cooling. So that's important because we want to know what is the efficiency, so it's important to characterize what is money and what is waste. All right, so this said, what is the efficiency? The efficiency is W divided by QBC. So it's going to be equal, if you put in the numbers, you will discover that this is equal to 1 minus TD minus TA over TC minus TB. Ah, what a great result. Instead of having the ratio of 2 temperatures, now I have 4 temperatures. Magnificent. So what can I do with this? Well, one thing I can do is I can use the relations in the adiabatic parts between temperatures and volumes in order to transform these relations in terms of ratios of just 2 volumes. Because, you know, notice one thing in this cycle, that here I have essentially I'm operating not between 2 temperatures, but between 2 volumes. I have the larger volume and the smaller volume, right? I don't have the larger temperature and the smaller temperature. So that's why I want to rewrite everything in terms of the ratio of volumes and not of temperatures. So how do I do that? Well, I notice that TA VA to the power gamma minus 1 is equal to TB VB to the power gamma minus 1. So this is the first adiabatic compression. And then TC VC to the power gamma minus 1 is equal to TD VD to the power gamma minus 1. This implies that TD is equal to TC VC over VD. Well, VC and VD is the same. Sorry, guys. Let's skip writing useless things. So VD is equal to VA, and this is equal to VB. Right. So, well, if you solve these 2 equations, then you will see that TD minus TA is equal to TC minus TB times VB over VA to the power gamma minus 1. All right? And this implies that the ratio that is written up here of these temperatures comes out to be equal to, let's write it here, eta equal to 1 minus VB over VA to the power gamma minus 1. Or in other words, this is 1 minus 1 over R to the power gamma minus 1, where R is the ratio of the largest volume to the smallest volume. Okay? So it's essentially, when you think about the piston that is moving in a cylinder, is essentially how much volume is the piston covering in its excursion in the cylinder. And it's obvious that, you know, since this is the movement that is then generating the torque that moves your wheels, okay, it's obvious that this should enter in the efficiency of your engine. Great. So this is called the compression ratio. Compression ratio. Now, what is the compression? So can we use this to estimate the efficiency of a car, of my car, my 3-cylinder car? So let's say that we take a compression ratio equal to 8. Okay? Now, gamma depends on the substance, because it's essentially gamma minus 1 is the ratio of the difference between constant pressure and constant volume specific heats to the constant volume specific heat. So I don't remember where I got this number, but I got gamma equal to 1.4, which is probably for something that looks like a gasoline, even though it's a bit of a cheating, because when you fill your piston, your cylinder with gasoline, is not that you put in the liquid, right? You don't put in liquid gasoline otherwise. What you do is there is an injector that sprays some fuel in the cylinder, and then you have a mixture of this fuel with air. So I don't know what is the gamma for this mixture, so that's why I put a number that is probably not very accurate. But anyway, let's see what comes out. Eta is going to be equal to 1 minus 1 over 8 gamma minus 1, which is 0.4. And if you take this, you will get 56% of the efficiency of your engine. Now this is a lot. It's way beyond anything that a real car has. Real car has 20%, 30%. When you pay a lot of money for oil, for gasoline, most of that money is wasted, okay? It would be more efficient. I don't know what is the efficiency of the human body, but I'm sure it's higher. That is actually something interesting. That one can, the human body is essentially an engine. I mean, if you see it thermodynamically, you put in food and you walk, right? You're walking. So you could ask yourself, how efficient is this engine? I don't know if it was ever asked. I leave it to you as an exercise. Again, check in Wikipedia or on the internet with Google what is the efficiency of the human body. I have no idea what is the answer. But for a car, is very low, typically. A good Ferrari, the Formula One cars, get pretty high efficiencies, which are close to 50%. And this is really enormous, okay? It's really a lot. Now, in that case, the article I was reading this morning said that if you estimate if you estimate what is the maximum Carnot efficiency you could get for the Formula One car, which is not a thermal engine, by the way, it's much more similar to this one. It's certainly not a thermal engine, but by estimating the difference in temperatures by the temperature of the explosion and the temperature of the exhaust, which is the explosion is 2500 degrees Celsius and the exhaust is 600 degrees Celsius, you could get a Carnot efficiency of 68%, and they get 50%. So, well, you can enjoy yourself, right? I mean, I give you some. All of this is, when I was told this stuff in school, it was so boring. But when you see it with the practical eye, it's actually interesting, right? Because you can see at every single engine that you're operating as something that is following the laws of thermodynamics. And actually, knowing what is the efficiency is important. It's not a waste of time. All right. So next time we will do the diesel cycle. Okay? We'll start with the diesel cycle and then we will do many other things. All right. I will send you the notes later and everything else. Don't worry. No, because I keep getting emails, right?